Hi, my name is José Pombal, and I'll be presenting Understanding Unfairness in Fraud Detection through Model and Data Bias Interactions. The main motivation for this work is that in recent years, machine learning models have been more and more used in high-stakes decision-making applications. And a lot of these applications are actually in the financial domain. So our use case, for example, is fraud detection. And also a popular use case is consumer lending. And so there's a lot of concerns about how these models might make biased predictions, and we've seen that they do, and how these predictions will serve then to exacerbate existing social inequities between groups in society. Now, this has given rise to the field of fair ML, but most research in the field is focused on measuring fairness accuracy trade-offs and developing tools to mitigate unfairness according to some sort of fairness metric, while there is actually little focus on the underlying causes of algorithmic unfairness. So asking questions like, why is my model making biased predictions? Is it a problem with the model? Is it a problem with data? Is there some sort of bias in my data set? Is it an interaction? And there's also a lack of definitions to go ahead and characterize these types of biases, in particular data bias. There's a lot of historical and philosophical definitions, if you will, not a lot of measurable, tangible definitions of data bias. So our main contribution to this discussion is first a taxonomy to characterize data bias involving a protected attribute, other features, and the target variable. Then to show how unfairness is a product of an interaction between data bias and models, we train a diverse set of models on several data bias settings that are inspired by real world fraud detection setting. And we show how the landscape of fairness trade-offs and fairness accuracy trade-offs, so that is the trade-off between fairness and performance and the trade-off between different fairness metrics, how that landscape changes with each combination of data bias and model. So to start off with our bias taxonomy, we begin with a base condition that states that a dataset is biased if the joint distribution of its features and its target variable is somehow dependent on the protected attribute. Now, this is a bit vague of a condition, not really measurable, but it can be unfolded into more measurable conditions, like prevalence disparities, which, for example, states that one group has a higher fraud rate than another. Group-wise class conditional distribution bias, that states that the feature distribution of a group is different from that of another group. So let's say maybe for a given group, some features are more informative of fraud, and so the classifier has an easier time detecting fraud for observations of that group, which will generate unfairness in terms of error rates between groups. And noisy labels bias, which states that some observations have been incorrectly labeled, and in particular that one group suffers more from this than others. So one group has a higher rate of noise, if you will, than other groups. And throughout this work, we're working with binary protected attributes, but these definitions stay the same for any type of protected attribute, be it categorical or continuous or multi-label, so a combination of several attributes. Then we also have some bias extensions, which are like conditions, but they do not imply the base condition. The first one is group size disparities, which states that there's just a larger group and smaller groups. So for example, there's a majority group and a minority group instead of being 50-50. And train test disparities, which allows for the biases that are contained in the data set to be different from training to testing. So obviously, we hope that the training and testing distributions are similar, but this might not happen, and that is also the case with bias, and we have to take that into account. So the main methodology of this paper and the idea is to take a seed data set, an account opening fraud data set, inject it with biases corresponding to a series of hypotheses that we said at the beginning about unfairness and data bias, and see for each bias what is the unfairness. So measure the unfairness that the models exhibit and the trade-off between accuracy and performance that they exhibit. And we inject these biases synthetically to be able to fully control the bias that is in a given data set to be able to then draw the causal link, if you will, between bias and unfairness, to say having this type of bias along with this model choice leads to this landscape of unfairness and performance. So our first hypothesis is that group size disparities alone do not threaten fairness. And we find that on average they don't. This is a series of models we trained on the data set. On the y-axis is fairness and the x-axis is performance. But we find that from left to right, as the disparity grows larger, so as you have an even bigger majority group and an even smaller minority group, the variance in fairness actually becomes larger as well. Simply because the minority group has a small sample size, which might give you some variance in the metrics, in the group fairness metrics that we employ in the error rates. So then the classifier can harm any group. Our second hypothesis is that groups with higher fraud rates will have higher error rates, so that's like false positive rate and false negative rate, and in turn that will affect unfairness because the balance between these types of error rates is in itself a measure of fairness. And we find that in this case, actually, the group that is being harmed actually depends on the metric we use. On the left, it's the group that's being harmed is the one with a higher fraud rate, but on the right, it's actually the one with a lower fraud rate. So this motivates the appropriate choice of a fairness metric for your task. Then hypothesis 3 is about how correlations with the sensitive attribute, so between the protected attribute and features, influence fairness. As it turns out, they do. And contrary to the previous hypotheses, the harmed group is always the same, regardless of the metric you use between these two. And it's the group for which the features are less informative. And also, simple unfairness mitigation interventions like unawareness or equalizing prevalence cannot be used sometimes, or if they can be used, they don't work as well as in previous scenarios. So you have to apply other techniques. Our last hypothesis about how noisy labels, specifically the ones generated by the selective label problem, where your system decides which labels you observe and which you don't, how this affects algorithmic fairness. And as it turns out, it affects insofar as it changes the balance of prevalence between groups. So if it generates an imbalance, then it generates unfairness. If it actually contributes to balance the ratio of prevalence, then it actually might contribute towards fairness. Finally, to look at models, if we compare some ensembles of trees with gradient boosted trees and random forests, we see that random forests in general seem to be more robust to variance, which is something that we talked about in the first hypothesis. And they seem to be fairer in general for most hypotheses, except for the third one, which is something to think about, the specifics of this algorithm in comparison to the gradient boosted trees algorithm. As for multilayer perceptron and logistic regression, they also show a very different landscape when comparing the two of them and comparing them with tree models. And obviously, this landscape depends on model choice and hyperparameter optimization, but these plots serve to show how really for the same bias condition, if you just change the model, you don't even need to change the data, you might have quite different performance and fairness, and the relationship between performance and fairness might change as well. So to wrap up, we proposed a data bias taxonomy to characterize the underlying causes of unfairness. Then we modeled a series of hypotheses featuring data bias scenarios and tested a diverse set of models on each one. And we showed how the landscape of trade-offs changes significantly with each combination of data bias and model. We hope that this work inspires future research in this field, and we encourage you and invite you to check out the full paper for more details on the results and the experimental setup and on the work in general. Thank you very much.